Hello, I am Dr. Maxwell Boachi, one of the editors of this book and also the author of Chapter 19, Construct, Failure, and Prevention. In this chapter, we have four main objectives. The first is to understand why and how implants fail. The second is to understand the relationship between the stress, the bending moments, and the section modulus of implants. The third is to understand what is meant by cantilever beams and its application in spine surgery. And then fourth is to understand how the stability of constructs can be improved. We hope that after completing this chapter, you'd have a solid understanding of why spine constructs fail. If you remember anything at all from this chapter, is to remember that implants fracture and surgeons fail. Constructs fail because of three primary reasons. Either there is a failure of the implant, or a failure of the bone at the implant-bone interface, or failure at a component-component junction. A key principle to remember is that implants fail at the points of maximum stress application. So most of your implants in spine surgery are going to fail where they're experiencing the most or maximum stress. So in order to understand how you can prevent this, it is important to understand stress. Stress is related to the bending moment, M, and a section modulus Z, and is defined by the relationship stress equals M divided by Z. What is important to remember is that Z is proportional to the third power of the diameter of a rod, or the third power of the inner diameter of a screw. Therefore, straight versus tapered screws will experience different stresses because they have different inner diameters. It is important to understand the concept of cantilever constructs. What is meant by the term cantilever? Cantilever refers to a beam-like structure that protrudes or extends from a stable point to support or immobilize a segment of the spine. It is a beam that is rigidly supported only at one end and carries a load. There are two main types of cantilever beams described in spine surgery. There is the fixed moment arm cantilever and then a non-fixed moment arm cantilever. In a fixed moment arm cantilever, the implant or instrumentation is designed to maintain a constant distance or moment arm between the point of fixation and the segment of the spine being supported. In the non-fixed moment arm cantilever, the implant or instrumentation does not maintain a constant distance or moment arm between the point of fixation and the spine segment. The non-fixed moment arm allows for toggling at the screw interface, implant interface, at the point of fixation. The point of failure of a fixed moment arm cantilever beam with a fixed inner diameter is usually at the screw plate juncture. The first figure that is displayed here shows that in both fixed and unfixed cantilever beams, the bending moment increases linearly along the screw which is shown in the dotted line in both figures. The solid lines depict the stress, which is the bending moment divided by the section modulus, which is unchanged along the length of the screw for a fixed diameter screw, but rises exponentially for a tapered inner diameter screw. As a result, for a fixed diameter screw, the fracture would be at the screw implant juncture, the screw plate juncture. Whereas in a tapered screw, the fracture would occur usually at a point of maximum stress application, or in this case, close to the tip of the screw. It is important to understand the different types of forces experienced by a fixed versus a non-fixed arm beam. In a fixed cantilever beam, the forces experienced are perpendicular to the long axis of the screw. In a non-fixed moment arm beam, the forces experienced are more three-point bending forces as shown in the figure below. In this figure, you see that the bending moment is maximal at an intermediate point of fixation. Next to this figure is a radiograph that shows a fracture of the screw in a non-fixed ventral, non-fixed implant. We see that the fracture occurs at an intermediate point of fixation where the bending moment was maximum. Hopefully this gives you a good understanding of the differences between the fixed and the non-fixed cantilever beams as you plan your spine surgery constructs. A related concept is the long segmental, multi-segmental fixed cantilever constructs. Given what we said, most fixed moment arm multi-segmental constructs would tend to load the caudal screws more than the rostral screws. Therefore, most likely, fractures in such constructs will occur at the caudal screws and not the rostral screws. The main disadvantage of the non-fixed cantilever beams, or one of the main disadvantages, is that toggling of the non-fixed moment arm cantilever beam screw in bone can degrade the integrity of the bone as well as the integrity of the screw bone interface. This phenomenon is called a windshield wiping phenomenon. It may result in the screw itself abutting the end of the bone graft, thus obliterating a portion of the surface area of contact between the bone and the vertebral body, as shown in the figure shown here. The final figure, two figures I want to show, illustrates how we can improve the integrity of implant bone interface. This integrity can be optimized in many ways. As you know, the ability of the implant to resist failure is in part related to its ability to distribute loads. This is called load sharing. In load sharing, no single portion of the implant or spine bears an excessive portion of the load or load bearing. In other words, it is optimal if applied loads are distributed over multiple implant components and multiple points of contact with the spine, i.e. load sharing. This can be accomplished by 1, improving the integrity of the existing implant bone interface, for example, through screw geometry and triangulation, which is discussed in other chapters. 2, providing additional bone interfaces through the provision of additional points of fixation, which would help provide the ability to resist deformation in more than one plane and by more than one mechanism. In the figure shown here, we see that the addition of the intermediate point of fixation significantly strengthens the construct and helps it resist translational and rotational forces versus just axial forces as shown in D. So in E, there is a second intermediate point of fixation, and that helps provide the additional stability. Another way of improving the implant bone interface is to strengthen the integrity of the bone. So it's very important that surgeons optimize the quality of the bone, treating any osteoporosis, treating any underlying bony disorders, optimizing the patient's medical condition in order to get the most optimal bone health before instrumentation. A final way is to normalize the geometry. If surgeons don't pay attention to geometry, which includes removal of anterior osteophytes, implants may not sit flush with the spine, and this can create conditions for implant failure as shown in this figure. So we hope that this chapter has given you a good understanding of the reasons why constructs fail and how and why you can optimize your constructs for the best stability. It's important, as mentioned, to remember that most of the time implant failure is more due to surgeon failure. It's important to understand the 4 main reasons implant fail, which we discussed, and understand the relationship between the stress, the bending moments, and the section modulus in understanding how different screw designs would experience different stresses. We discussed the fixed and the non-fixed moment cantilever constructs as it applies in spine surgery. And then finally, we looked at examples of how you can optimize your implant bone interface through appropriate screw geometry, triangulation, optimization of bone health, and understanding the gardening of the spine to ensure that the spine implant contact is ideal. So in summary, we want to emphasize that implants fracture, surgeons fail. We have looked at the different mechanisms of failure of spine implants. We've looked at how to optimize the stability of the spine, and we went over the cantilever beam constructs. We hope that these concepts have provided you with a good understanding of how and why implants fail, a good understanding of the relationships between stress, bending moments, and section modulus, and that application of these principles would help you to become a more proficient an expert spine surgeon.